Good morning, good afternoon, good evening from wherever you are calling from or wherever you are listening to this recorded session. Welcome to the weekly science review. This is our weekly science review 13, and I will be leading the discussion today. And myself, Ayyappan Alangovan, and I'm a research scientist at Vetri Labs. Weekly Science Review is a weekly event organized by Vetri Labs where we focus on open access journals published in electrochemical science and technology, and we'll be discussing that. Can you all see my screen?
Yes.
Yes.
Okay, yeah. Today's paper is oxygen functionalized cobalt phosphide nanowires as high efficient and stable electrocatalyst for oxygen evolution and full water splitting. So electrocatalytic water splitting technology. So we all know that there is a huge depletion of fossil fuel reserves, and at the same time we are creating some environmental problems because of using fossil fuels. So there is a huge demand in green energy, and water splitting definitely has interest. It received many interest towards energy storage and conversion. And the kinetic limiting factor of the overall water splitting is this OER reaction because it involves breaking the two of OH bonds and also the one attendant O double bond O formation. Mostly precious metal oxides have been reported to be the most effective electrocatalyst. However, they suffer from high cost and also they have a poor chemical stability in the alkaline solution. As a result, people have tried to identify other electrocatalysts, and the transition metal-based catalyst has played a significant role in the improvement and also on the cost reduction. So one of the important thing that they focus is the transition metal phosphide hybrids. So they have either focused on tuning the stoichiometric ratio of the metal and the phosphorus or introducing any heteroatom doping or alloying, or forming these nanocarbon hybrids or engineering some special structures by modifying the surface and also forming other heterostructure interfaces and generating some porous structures. So out of all these transition metal phosphides, cobalt phosphide has emerged as a promising and noble metal candidate for water splitting because of its low cost, high electrical conductivity, and its remarkable HER activity. However, its oxygen evolution activity is very inferior, and also and it also suffers from other issues. One of that is the pristine COP crystals has like large oxygen absorption free energy. So in that case, you will need a large overpotential to overcome the energy barrier. And the other problem is the surface atoms of the COP crystals will react with the alkaline electrolytes, leading to some changes in both the structure and the morphologies, which will have the negative effect on your stability of the electrode in the alkaline solution. So this current study is focused on generally producing oxygen functionalized CoP nanowires, and then they have reported this to be a stable electrocatalyst for OER and overall water splitting. So their assumption is so functionalizing with oxygen atoms can help to redistribute the electrical structures, and that could eventually decrease the Gibbs free energy, making the breaking of this OH bond and also forming this O double bond O will be much easier. Next, the introduction of these oxygen atoms can also enhance their conductivity of this pristine COP nanowires because the oxygen atoms can reduce the contact angle. So that can give you a better charge transfer and mass transfer. Also, the growth of this electrocatalyst on this carbon cloth can provide you the direct electron transfer path and also the medium for gas transport, and can also avoid unwanted interface between your collectors and electrolytes. So the electrodes preparation. So in general, like they have used 3 millimolar cobalt nitrates, 6 millimolar water, 8 millimolar NH4F, and then 50 millimole urea, and dissolved in 50 ml of DI water. Then they transferred this 20 ml of the above mixture to a Teflon autoclave of 30 ml, and then they also put a piece of carbon cloth, which was already cleaned. And then the autoclave had a hydrothermal treatment at 120 degrees Celsius for about 6 hours. And then the formed COOHF on the carbon cloth was washed with deionized water and ethanol and dried at 60 degrees Celsius overnight. Followed by the hydrothermal method, you will have this cobalt hydroxide with fluorine doped on this carbon cloth, and then they undergo phosphorus doping at 350 degrees Celsius for 2 hours in argon in the presence of NaH2PO2. And then as a result, you form the CoP nanowires that are supported on this carbon cloth. So to form this oxygen functionalized CoP nanowires, they tried to do it anneal it in a mixture of argon and oxygen at different temperatures to see how the annealing temperature impact the activity. And as a result, you form this oxygen functionalized CoP nanowires attached to this carbon cloth. And the loading of this cobalt phosphide was identified to be 4.38 milligram for this pristine CoP nanowires. And for the oxygen functionalized, it was found to be 4.66 milligram per centimeter square. So they did some material characterization to confirm the morphology, and what they could see is the formed CoP nanowires were about 250 nanometers in diameter, and even after annealing, they were able to retain their morphology. And with the TEM, they were able to confirm the internal lattice fringes were about 0.189 nanometer, corresponding to this 2-on-1 plane of CoP, confirming the presence of CoP particles in their structure. And also with the elemental mapping, they could demonstrate that the distribution of the cobalt, oxygen, and phosphorus, and it was uniformly distributed throughout the nanostructure. So which could eventually confirm the doping of oxygen and also the phosphides. Next, the material characterization. So then followed by that, they did this XRD patterns and then identified that for different annealing temperatures or just the pristine nanowires, they all had this characteristic COP peak at 25 degrees. And also they didn't have any other peak, suggesting that they were all high purity. And also to, since the carbon cloth has a larger weight, so they did the TG analysis to study the oxidation process in the presence of oxygen. As we see in this right side figure, as we can see, as the temperature increases, there is an increase in the weight percentage, suggesting that the oxygen is reacting with the COP nanowires under this anneal process. Next, they did some XPS analysis to confirm the elemental composition and the surface chemistry. And as you can see on the first one, the peak intensity and the area of the phosphite in the OCOP nanowires was predominant, right, on the compared to the COP nanowires around this 130 to 135 EV, indicating that new PO bond was created. Next, on the cobalt one, they have two peaks, and the first peak can be split into two peaks, which is at 778.9 EV, which is the COP bond, and one is the cobalt oxide bond at 782.05 EV. Also, this ratio decreased after the annealing process, and the peaks of this O1 on the oxygen spectra, the peak where there was two peaks that was centered at 531.3 EV, which was the cobalt oxide, and the phosphorus oxide was centered at 532.9 EV. And the binding energies of both this peak was shifted by about 0.2 EV when you functionalized with oxygen. And that corresponds to the shift because of the oxygen functionalization. And also they did the Raman spectra, and they could find the characteristic peaks of cobalt oxide on all the like oxygen functionalized cobalt phosphate nanowires or just cobalt phosphate nanowires. And the cobalt oxide are functionalized, like the oxygen functionalized cobalt phosphate nanowires exhibited like a similar peak shift as cobalt oxide. So which means there is an existence of this cobalt and oxygen bond. And also there were like stronger and broad peaks around 900 to 1000 centimeter inverse, which was attributed to the presence of P bond O. Next, they did the electrochemical characterization using the linear sweep voltammetry to study the oxygen evolution activity. And what they found out is to generate a current of 10 milliampere per centimeter square, the oxygen functionalized cobalt phosphate nanowires takes very least over potential of about 265 millivolt compared to the best performing catalyst of ruthenium oxide. And also the pristine COP nanowires takes about 392 millivolt to produce even the 10 milliamp per centimeter square. And also the Tafel slope is about 68.4 millivolt per decade, which is almost close to the commercial ruthenium oxide catalyst. And also, if we see on this LSV at a higher current density of 50 milliampere per centimeter square, or even at 300 milliampere per centimeter square, the over potential for the oxygen functionalized cobalt phosphate nanowires is relatively lower compared to the ruthenium oxide. And so as we can see on this plot over here, they've plotted the over potential and Tafel slope for different cobalt phosphate catalyst, and they claim that their catalyst has about very low over potential compared to all other cobalt phosphate catalysts. And then, so this was grown on the carbon cloth, right? So they want to test how does the flexibility affect the activity. So they tested the electrochemical activity while keeping the electrode flat and also keeping it bent. And what they found was they don't have any change in the activity, making it almost like they match each other. And then they did the stability test. And so the stability test was done at a current density of 10 milliampere per centimeter square and 50 milliampere per centimeter square. And what they could found out was that the potential didn't change much for both the current density for this oxygen functionalized cobalt phosphate nanowires. But whereas on the ruthenium oxide, even at 10 milliampere per centimeter square, even after 10 hours, there is a 200 millivolt shift in the potential. And also they compared the morphologies and the XPS spectra to see how it got preserved over this long-term study of about 50 hours. And they were saying that there was no change, making it having good stability, and also the electrode was very well preserved. And they did the over potential for the oxygen functionalized cobalt phosphate nanowires and how the temperature, annealing temperature, like influences their activity. What they saw was the initially decreased with the annealing temperature, and however it decreased and then it increased. So then the lowest over potential was obtained for this oxygen functionalized cobalt phosphate nanowires in red, which was annealed at 500 degrees Celsius. Then they measured the charge transfer property, and so the double layer capacitance was about 1.02 meter square, whereas for the cobalt phosphate nanowires it was about 0.86. So what this tells you that when you have a higher double layer capacitance, it means you have a larger electrochemical surface area. So as a result, since this cobalt phosphide nanowires are functionalized with oxygen, this could significantly increase the number of active sites in your electrocatalytic reaction, and hence you have a higher double layer capacitance. Next, the oxygen functionalized cobalt phosphide nanowires on carbon cloth had a relatively smaller charge transfer resistance, as we can see from the EA spectra. Also, in addition, they measured the contact angle for the cobalt phosphate nanowires and the oxygen functionalized cobalt phosphate nanowires. And what you can see is the one with oxygen functionalized has a relatively smaller angle, 18.22 degree, whereas the other one has 132.82 degree. So the smaller the contact angle, you will have a better wettability, and at the same time you have like an effective contact between your electrode surface and electrolyte. As a result, you will have an easier mass transfer and also a smaller charge transfer resistance. And so the ultimate aim of this paper was to kind of put this oxygen functionalized cobalt phosphate nanowires as catalyst on both the sides and run the overall water splitting. So for that, they wanted to test the HER activity. And the oxygen functionalized cobalt phosphate nanowires had a a comparable activity to their pristine COP nanowires. And they try to put a full cell together. And as we can see here, for comparison, they also put a platinum carbon and ruthenium oxide put together to form a full cell. And as we see here, the overall potential was about to achieve a current density of 10 milliampere per centimeter square was about 1.66 volts. Whereas when you want to obtain a current of about 20 milliampere per centimeter square, it's 1.72 volts for the oxygen functional cobalt phosphide, and whereas it's 1.85 volts for 50 milliampere per centimeter square. Whereas when we compare for the platinum carbon, all this potential is shifted relatively to a high, and there is a higher over potential for these current density. And also they wanted to test the stability at different current densities for a total time of 10 hours. And they saw almost they have a good stability even for 10 hours, even at a higher current density of 100 milliampere per centimeter square. And they have also measured the Faradic efficiency, and they found out it was close to 100%. Then in summary, so the OER activity and the durability of this cobalt phosphide nanowires with oxygen functionalization helped, and also the ratio of the surface oxidized cobalt phosphide can be adjusted by tuning the annealed temperature, and the optimized electrode annealed at 500 degrees Celsius was able to deliver a current density of about 10 milliamp per centimeter square with the over potential of 265 millivolt and a Tafel slope of 68.4 millivolt, which is comparable to the metal oxide catalyst and superior to most of the cobalt phosphide catalyst. And they also possess extraordinary stability and kept its original structure after a long-term test of about 55 hours, even at a constant current density of 50 milliamp per centimeter square. And this high stability is attributed to its improved surface area and also its effective charge transfer and decreased free energy due to this oxygen functionalization. With that, I would like to thank you all, and then we can start the discussion now. Yep. If you guys have any questions or
Like, did they talk about how did they find the loading? Like,
no, I was trying to find those information. I had the same one. I wasn't quite sure. I mean, how the loading calculation was done. I would think their carbon cloth seems to be pretty large. So I think they might have just used analytical balance to take the weight difference is what.
before and after. Okay.
Yeah, because it's definitely when I look at it, I mean, at least on the image wise, I'm sure it is about like 3 or 4 centimeters square. So you can definitely see that when they talk about 4 milligram, 20 milligram, probably they could just use the balance is what I would think. Yeah.
And also one more thing is the carbon cloth did not decompose even after annealing it like without.
Yes.
I mean, with the TGA, if I see the data, it does not decompose. That is little.
Yes. Yes. Yeah, I
Mm.
It will
had
not
that.
decompose. Carbon cloth, it will not decompose.
It
Yeah,
should.
I wasn't sure. I mean, later then I added when I was looked at the TGA, I wasn't sure. Then I was like, yeah, that is what I was about to bring that point up, and also the HER activity. Somehow, because all cobalt phosphide or any cobalt catalyst seems to have a very high HER activity. I wasn't sure how after oxygen functionalization, their over potential could not match the pristine COP nanowires. And they haven't commented on that.
I think that's the reason they didn't compare it with commercial PT bar C. They just compared with PT plate.
Yeah,
So it's a
PT
bulk,
plate.
so it doesn't
Mhm.
make any fair comparison. Yeah.
Yeah. Even with the, so when their whole idea is like with the oxygen functionalization, their conductivity is improved. But I don't see the correlation
Yeah.
how their HER activity decreases after they functionalize with oxygen, because they did the IR correction. When I compare, it's about 150 millivolt over potential, higher than their pristine cobalt phosphate nanowires. So yeah, I had those two on mine when I was just going through this.
And also the double layer capacitance comes from the carbon cloth. I
Mhm.
don't know how they are connecting that with the cobalt phosphate.
Contact angle.
Yeah.
Actually, it seems to be for both it has to come below 90. For one thing, it is came above 130. That means it is not coated at all. Because you showed the same image, it is our same image. It's like a rough surface.
Yes.
So when the surface is rough, you cannot get hydrophobic nature. It will be hydrophilic because of roughness itself, not because of material.
Mhm.
So in the second case, when oxygen functionalized, it's fine because it's below 90.
Yep.
That
Yep.
means it's completely hydrophilic. And they have claimed that because of hydrophilic nature, it can happen, double layer can increase, but activity it will decrease. Electrochemical activity, it has to decrease.
Yeah, their climb of the contact angle is like their charge transfer resistance will drop and their mass transfer would be easier. Is there what they climb when they have a very low contact angle?
Yeah, they have did it in a flooded cell, so it will happen. When they do it in a full cell, it will not happen.
Yeah.
That is the thing. So that is the contradictory statement. So I cannot comment on it. But still, in a flooded system, it's fine.
Mhm.
And another thing is that the TGA. They mentioned that it's a oxygen functionalized one, right? You have did the TGA in air itself for oxygen environment, so the weight should not increase between up to 600 because they go annealed at 400, 500, and 600. That means it's not completely oxidized.
True. True.
Still, it is further getting increased. Weight is getting increased after I think 250.
Mhm.
It's completely going up. That means it's partially functionalized, not completely functionalized. There may be a vacancy in that sites that they have not properly explained.
Yeah, there were a couple of places where I felt when they could have done proper justification on explaining through. Some of them were just had a conclusion, but there was no probably like an explanation behind how they came to that conclusion. Was just missing on this paper.
The activity wise, it's fine, but stability also it seems to be good because there is no decline in the performance.
Yeah.
Still, the chemical structure it has not been properly elaborately explained in terms of activity.
Yeah,
So
yeah, true. And also, like they've done a good job on trying to take those
yes,
PS post and post stability and like a post electrochemical test, and after that, and then seems to see how the if the structure was preserved or not. So those were done, but kind of couple of their correlations for their activity with their material characterization doesn't. They are contradicting, as you mentioned. They don't go on the same page. Yeah. Is that all? Is there any other questions or comments? Okay, so if that is the case, I'd like to take you to this. Okay, so next week we'll be discussing about synthesis of dimeric molecules via silver catalyzed electrochemical homocoupling of organic bromides paired with electrooxidation of urea. And thank you, everyone, and see you all next week.
thank you all.
Thank you.
Thank you.